Okay, we'll go a bit through how we see infrastructure as code and how the movement or the evolution is progressing towards platform as code and why. Then we'll talk about why Kubernetes is actually not just a platform, but a platform for building platforms, and showing some examples how building blocks are evolving here through the community and also here at GiantsForm for building Kubernetes platforms or building platforms with Kubernetes. And then we'll just close the session with some challenges and a vision and an outlook where this journey will be taking us. But let's start at the beginning. First, we have almost 11, and for those in Germany, today is Altweiber or Vive Fastelovend, like we call them here in Cologne. So Alav and happy Carnival to you. But enough fun. Let's go to infrastructure as code. Where are we coming from? And infrastructure as code, the definition is not that clear, right? We start at machines. Everyone agrees machines or virtual machines should be infrastructure, then networks, load balancers, storage. Most of the time you would include DOS. Would you include Kubernetes? Would you include the CNI, DNS, and security on top? If you ask the infrastructure as code providers, most of that is included. But it's not important what you are including there. The more important part of the as code is that we are looking at codified infrastructure, right? We want to have it descriptive. We want to have it repeatable and shareable. And to an extent, we want to have it automatable, even if a lot of people are not automating it, be that because of processes in the company or be that because of risks that an upgrade or a run of this infrastructure as code tool has inherently because of, I don't know, some issues that you might run into. But the goal of why we came up or why the market came up with infrastructure as code tools was to use similar processes and similar tooling that we are already using in software development. So the areas get closer to each other. We using IDEs or editors. There can be code reviews on the code that is describing your infrastructure. And that can be even versioning, or if you're very modern, kind of a GitOps approach, right? And as most of you are using one or the other tool here, we don't need to go into much details, but there's some differences in the way and the method of pulling or pushing the configuration. And there's usually a declarative or an imperative approach, although like most of these tools, especially the older ones, they started at imperative and they went towards declarative, where you really declare what you want to have and don't run scripts only through the servers. And from there, we are kind of moving towards, and this is also pushed by the infrastructure as code providers, towards having more of the platform defined as code. And the goal of that is building PaaS-like systems. Right? Some of you might be using PaaS also, but what we're seeing a lot is that people are following this platform as code approach to build platforms for their own companies, for especially the bigger they are. And the goal of these PaaS-like systems is, the main goal is an abstraction layer. And the abstraction layer is not just there for itself, it is to enable the developers, the end users, the engineers to focus on their code and not have to do that much heavy lifting and learning on the infrastructure side. And for most companies, there's also some component of self-service in there. So the safer it is to use, the more abstracted it is, the easier it is to give out, and you don't need to fill out 17 pages of forms, hopefully, to get a server, but can just deploy your code and have some way of safely doing that. Especially in the enterprise, if you're looking at bigger companies, there's also a lot of standardization and sharing of common practices as a goal. And definitely also security, not only in the enterprise, there may be more enforced, But this is a really important thing also, and a really good benefit that you can gain from building platforms is to enforce, or at least ensure or motivate some security, some base security towards engineers. But there's also some pitfalls or downsides that a lot of traditional paths used to have, and that when you're building your platform, either in do-it-yourself or with some building blocks, or even taking a full platform from a provider, you want to be careful about these things, because the nature of abstractions is if you cannot poke through them, they will at some point have some limitations, right? That's the nature of why you're abstracting. So you're limiting your users, and this is okay in most cases. But at some point, as the software itself grows, as developers are maturing, they might hit some limits. Like some use cases might hit the limits of what you have built as an abstraction. You might need to rebuild the abstraction, poke it through a bit. And if you don't, if the abstraction is very strict, and or it's a platform that you don't have control over, like the typical case out there, Heroku, a lot of us have built systems on Heroku, hit the limits, and then we build workarounds. And those workarounds usually get quite ugly, or they're definitely not intended because they're workarounds, right? And in a way, if you had a pass in the past, I mean, we're not having or had not the ability to build it yourself, you were quite locked in because you had built right for Heroku. And moving from Heroku to EC2 machines, for example, there used to be a big project. And then there's something new coming up, actually. What we're seeing is that a single platform might not be enough anymore. We're getting to a place where even inside middle-sized companies, you have very different kinds of engineers. You oftentimes now have data science engineers, and your data science engineers might have very different needs towards a platform than your web scale e-commerce engineers, for example. And you might have both in the same company. You might have even more types and variations of developers and engineers that have needs, and they might need different things. They might need a function as a service might be better for them, or some very opinionated AI platform might be really good for them.
Puya, can we just quickly add a question that came up, which I think is a good time now?
Sure.
The question was, what exactly do you mean with platform?
That is a good question, actually. And I do think that platforms, yes, AWS could exactly be a platform, because AWS does, for example, have Lambda, and they have EKS to run your Kubernetes workloads. They have Beanstalk. They have a lot of services. However, you can also use AWS as a building block inside your platform, because sometimes you want to have more than that. Like you want to have maybe like you don't want to have your engineers, or your engineers might not want to actually work directly on AWS. They want to maybe just have to do with your GitLab. They want to just push their code, and there is a different team that is building maybe the CI/CD pipeline, and that is part of the platform, I would say, to see where that code gets deployed and how that gets deployed. And you need good, and there will be hybrid solutions, and that's exactly the point where a single platform might not be a great solution. And I also think that Kubernetes in itself is not enough as a platform. But we can talk about this in a bit, maybe more. Because does that answer the question? Yes, CI/CD. There is AWS service, or Azure has a very good deployment platform. I think so yes, the clouds do offer platforms. But again, when you're relying on the cloud, then you get into this single vendor approach, and at some point you hit the limits, and you will still need to build yourself. then let's continue to Kubernetes. Because some people stop at Kubernetes, say, okay, now we have Kubernetes, now we have a platform. Or now we have, we're all free and we can give that to all engineers and we're all happy. But if you look at how Kubernetes was intended to and how very prominent people in the ecosystem see Kubernetes, is that Kubernetes is the platform that you use for building platforms and for building also the abstractions and not being directly locked into a provider, hopefully, but having it abstracted so that you have an API to talk to. But it's just a place to start. It's once you have Kubernetes, it's still for most engineers, and it should maybe be for most engineers, not needed to directly interface with it. And just recently, one of the product managers from Microsoft, Gabe Monroy, was tweeting again. Everything is on Twitter right now, about that your engineers, or at least I think a lot of your engineers, might deserve more than just Kubernetes. They deserve a better user experience. And if you ask Joe Beda, he gave a pretty nice talk roughly 1.5 years ago, also about the topic of platforms, or Kubernetes as a platform. And there he talked a bit more about like why that is the case, why we see Kubernetes as a good start and a good building block to build platforms, and how we build all this extensibility into it. And that's exactly what we're going to show in a bit. Fernando's going to talk a bit more about the details, how to extend it, and why that is a good idea. So let's go into that. And also, when we say Kubernetes as an interface, we don't mean just for containers. And you will see that in the examples in a bit. But the reason for that is there is benefits as an orchestrator even without the container approach. Because on top of the declaration or the declarative paradigm that is also in Kubernetes, you have a reconciliation approach. Right? You have something that is taking your desire that you expressed in your declaration and making sure that is reconciled at all times. So that is, if someone goes and deletes your load balancer, something is going to recreate it. Right? And you don't need to rerun a script. You don't need to rerun your infrastructure as code tool. That is inbuilt, right? Or you can codify that. And what you can do on top, I mean, most infrastructure as code tools, exception being Pulumi, for example, are not full programming languages. So once you get into those places where you need a bigger migration within your platform, for example, let's say moving from Helm 2 to Helm 3, or moving from etcd to etcd 3, if you have been using Kubernetes for a very long time, you might remember that. Those were quite big and risky, and also quite manual migrations. And what we did, we codified them, for example. And this is something that with an orchestrator where you can write the controllers, like in Kubernetes, as we will see in a bit, is something that is actually even encouraged, right? And that's why some of the naming in Kubernetes also came about. Operational knowledge, to an extent, at least, can be codified. There's still a need for people. There's still a need for SREs and everything. But at least complex migrations don't need to be completely manual or semi-manual anymore. And one of the other benefits that we saw, for example, when we started to use Kubernetes, is that it's actually open source software. It's actually a multi-vendor open source project, and it's not a single vendor. There is no single vendor risk. Some of you might have followed the Elastic license change recently. And single vendor licenses or open source software has always some remaining risk, right? And there's some very big opinionation in there. That was something like Kubernetes, that is a community approach is definitely less there. There's still bigger companies who steer it, but no one can by now really control the gist of it. And as we're going to see in Fernando's slides in a bit, it's very natively extendable. One thing that I found out just recently, because we're running Terraform ourselves too. Like, it's not that we don't have any Terraform anymore at GiantStorm. We're trying to get rid of it with time. But yeah, we had just recently, last week, we had 2 state corruptions in different places with Terraform. And they were really, really, really painful. And that's where I kind of also realized that the storage in typical infrastructure as code tools is a storage of status. And the storage in an orchestrator like Kubernetes is rather a storage of desire. And the status is live reconciled usually. As long as the code is built in a way that can be recovered, then, for example, with tags in the cloud or something, you can recover your state without having to actually have a lot of backups. You should still have backups, that's still needed, but a state corruption is definitely a bit less of an issue than what I've seen, at least with, for example, Terraform. And I don't want to bash Terraform explicitly, not like in this tweet, but there is a lot of people who, even when they're quite happy using Terraform, or every time they run Terraform, they're a bit scared. I was always scared when I ran Ansible scripts. And then the other side of Kubernetes, which is for me the more interesting side because it's the user-facing side, is it's a really nice interface. And once you're familiar with the interface of Kubernetes itself, it translates to all the extensions too, hopefully. I mean, if you're building good extensions, then it translates very well. And we can see an example of that with Cluster API in a bit. And when you're an extension builder, it's also really nice because you get a lot of things for free. You get a lot of API features that you usually would have to use some tools for or build yourself. You get it for free. That's why we are replacing our old REST API with completely Kubernetes and giving that to customers. And also the other side of it is you can still use your infrastructure as code tools, but you can also then use typical CI/CD tools like Jenkins. You can move to something like Flux or Argo CD that are GitOps approaches, and you can choose. You have a bigger choice of tools once you have an abstraction like Kubernetes on top. And you see that a lot of companies have already been working on extending these things and extending them for their use cases. And by now, there's also some common standards evolving where we can see, okay, hopefully in the future, we will have a bit more independence and a bit better standardized abstraction and get features from vendors, but don't get too much lock-in.
Oh, oops, echo. So now I would like to talk about why it's so powerful Kubernetes API and the extensibility that it provides. Today we are going to focus on the 2 main approaches I think are interesting to highlight, but there is others. So I will show you what is custom resource definitions and controllers, which we call operator pattern. And also I will give you an explanation of what is an admission controller. But there is others, as I said. There is the extension API server, which is a way to extend the API of Kubernetes running a parallel API server with your own logic. And then the main API server will proxy request to your code API, depend on the path that you have defined. Then there is infrastructure extensions where third-party vendors, cloud providers can extend some capabilities of Kubernetes, for example, storage, networking, and device plugins, other things. So you can plug and play different type of volumes or things like that. Then then we have Cuba Ctl Plugins. Cuba Ctl is the command line tool of Kubernetes, and it's also extensible, and you can program your own plugins, and you can enhance the kind of the capabilities that comes built in the main CTL, and give your own use cases, right? But this is out of the scope of this talk, because we don't have enough time. We may be moved to another one. So let's start with custom resource definitions, the first part of the operation pattern. With the custom resource definition, we want to represent a new entity in the Kubernetes API. So the idea is for our users, developers, operators, we want to bring a new concept to the cluster. And this concept can be different type of infrastructure or application. We will see later. And this type of resource can be registered at any time in the API. So you can create your own resources dynamically in the API without having to compile the API and restart it. It's just dynamic registration. And what is great? Well, because the Kubernetes API brings a lot of built-in features that you will have for free. For example, you will have CRUD operations like create, read, update, and delete operations for granted. You will have a watch. You will be able to watch your resources, as we will see later why this will be useful. There is discovery options. You also can build authorization with the same tools that you do for the deployments or pods, like role-based access control. You will do the same for your own resource. You can program finalizers, so you ensure that the object behind your resource is really gone or is really deleted when you delete your resources. So it's a way to control the deletion of the resource. Also, there is metadata, like all the labeling and annotation that comes from free, and there is other also features that are really handy to have for free. Then the powerful of this custom resource is always, or almost all the times, comes together with the hand of the controllers, which is the next thing I'm going to explain to you. But before, let's see what it looks like, a custom resource definition. So for the ones that have experience with Kubernetes, this is the typical YAML, the typical configuration file that you use. But here, if you see, we have in the kind a different object, right? Name here is custom resource definition, which belongs to the API extensions version, and is the way that you say to the API that I want to register a new object. In our case, we want to register a MySQL object, instance object. So we are going to call it MySQL acme.co. And in the spec, we are going to define how it will look like. So we are going to say that the group is Acme. The group is kind of the signature of the object. We will say that this is our very first version, the B alpha 1. The object is going to be scoped by namespace, so it's not cluster wide, is going to live in a namespace. And then we have to provide also the kind of the naming, how we are going to refer to this object. So the kind will be MySQL. You can also list it by MySQL or MySQLs with S, the plural, and this kind of things that the API needs to function correctly. And together with this information, you can also provide an open API V3 schema, which is a way to kind of describe the spec of the object, at the same time that provides you a way to validate automatically the objects that your users, the developers, operators are going to create. So here, for the sake of simplicity, I just add one property that I call DSN for our MySQL object. And in the DSN, we just explain that this is the data source name, which stores the information for establish the connection to the database. We say that is a string, and also we can provide a pattern, which will ensure that we are providing the correct value to every time that we create or update the object. And this is also helping us to generate all the documentation of the API, right? So this is also coming with this nice benefit of having documentation for free. And then once we have submit the custom resource definition to the API, we can start creating right now objects. So as a developer, as a user, I can start creating objects, type MySQL. If you check, the API version is acme.co, so it's the group, the signature that we define, the version that we define, because you can have versioning, then you will see why this is useful. And then we can start creating objects like a user DB, which will contain labels like, in this case, environment production. And here we are defining the DSN that this object is going to have, right? So now the second part, the controller. And we will see why it's so useful together with the custom resource. And the idea is the controller is a piece of code that normally runs in the same cluster. And it's going to help you to automate usually tasks that before you have been scripted or manually executed. And will be wrapped in this piece of code running. And this is going to watch for events that happens in the Kubernetes API. So the Kubernetes API emit events every time that something happens. So you can watch for events of certain resource or custom resource. And then in this logic, what you are going to try is you are going to try to reconcile the state. So based on the spec that the user has created, in this case the DSN, you are going to try to match the real estate, right? You are going to create, in this case, a database, MySQL database instance with this connection structure. The cool thing of the operators or the controllers is that can be language agnostic, because at the end, Kubernetes is a RESTful API, and there is plenty of clients that has been built on top. So you can, I think there are plenty. You can create controllers on Go, which is the usually, but there is Python, there is Rust, there is Haskell. Haskell, I'm not sure, but I think there is even a Haskell client, so it's quite powerful. And this is the same kind of concept that is using the Kubernetes itself for the built-in objects. So for the deployments, the pods, or the precassettes, we are having also the resource, and together with the resource, we have a controller which is reconciling the resource. So let's see this in kind of a diagram, how this works. We have a developer in our left, and we have the MySQL operator that we have programmed in our right. Okay, running in the cluster. So this is a binary, a container running in the cluster, and then the developer decides to create a MySQL instance. So it needs a database, and in the database he defined the spec at DSN in our case, and he will watch or he will wait until this is created. So our operator, what he's going to do is hook into the Kubernetes API. Once the developer supply the resource, is going to be informed. It's going to check, observe the chain, and then it will analyze what is happening. Right? In this case, we are having a new object, and then it will act. So in the very beginning, it will create an instance, but also could happen that the spec has changed, the DSM has changed, the number of replicas, whatever. So it will reconcile all the time the state, right? In this case, our operator is creating an instance, a pod of MySQL, and always is updating the status property of the object. So if you have check pods or deployments, you always see that there is a status property, which usually is used to plot the status of the object, the real object. So if we move to kind of a pseudocode that I invent myself, it's not real code, sorry, we will have something like this. We will have a reconcile function and this kind of 3 steps. We receive the request, the event from the API, and the first step, we fetch the resource. So we have our MySQL custom resource here. The second step is when we analyze what is happening. Here we are checking if we have already created or not the pod or the stateful set, which the stateful set is the kind of object that you use for databases or for containers that need a state. If the API has no any stateful set with our name, then what I'm doing in the third step is creating one. So it's the act step, right? And I create a new stateful set, and I creating the stateful set in the triggering a request to the API, and I updating the status to say creating, right? So in nest loops, because this is continuously running and checking the state. In the nest loops, I can update it status to create it when the pod is running, when the stateful set is reporting that everything is good, right? So this is the operator pattern, which was the first approach I wanted to show you. And now I want to show you what is a mission controller. All of these extensions, or all of these approaches can play together. And you will see that in some cases, in some projects that we will see later, is what actually they rely on. So an ambition controller is a piece of code also, usually running in the cluster, could run outside, but the kind of in the normal approach is always running in the same cluster. And the mission controller is intercepting requests in the API. And it's intercepting requests to provide you some value. In this case, it helps you with the validation, the defaulting, and the mutation of the objects. It only works for write methods, so it will be triggering the create and update, delete, I think, objects. And it's always happening before the object is persisted in the cluster database, okay? And Kubernetes comes with plenty of controllers, admission controllers, built in the own API. We have controllers to check the namespace is fine. We have controllers to check the container image is always a pull or not, and this can be enabled or disabled in the manifest or in the options of the API. But also you can extend those controllers. You can use something that is Workhook configurations to decide that you want to run also some of this extra functionality for your own purpose, right? And this is what we are doing right now. First, I'm going to show you this kind of diagram to understand what is the workflow of the request in the API. We see that the first we receive in the left the request in our kind of handler. So the API server has a handler, and always the first thing it does is check that this request is authenticated. So the user, the client behind, is it provides the right credentials. Then it goes to the authorization part, which checks that with the user can perform this action against the resource. And when this is accepted, it moves to the mutation or the mutating admission controllers. And the mutating admission controller is when we do all the defaulting. So properties that has been not defined for the user can be added at this moment, the default property, but also can be used, for example, to inject a sidecar container. So this is something commonly in service meshes or others, where inject additional container in your pod, for example, to inspect the network or give it you more additional value. When this mutation is done, then is when it triggers the object schema validation. And if you remember, we have defined a schema for our custom resource. So here in this step is when the schema is going to be check to be that she is compliant with the schema and can be rejected or not. And if it's accepted, then it's moving to the validation phase where we run, or the API run, all the validation controllers that are enabled for this type of resource. And it can be the built-in controllers, or it could be the webhooks that we have. And it's going through all the webhooks that is matching this type of object and operation. If all the validator controllers are okay, then the object is part of the cluster. It's persisted to etcd and is going to be part, and it's going to emit events and all the stuff, and controllers can start to reconcile the state. So let's see how looks a validation webhook. This is one I created for the MySQL example. And here you see that the kind is validation webhook configuration. And in the spec, where we define how it will behave, we define first where is running the piece of code that provides the logic to validate this resource. And here is where you define the client config service. So we are running the validator in the same cluster in a service that is called MySQL Validator Server in the namespace MySQL. Okay, and also we provide a cert, a CI bundle, to make that the API server and our validator authenticate the connection between the request. And also we are saying that we only want to validate these operations, create and update, against the resource type MySQL. So it's going to send us only requests that match these operational resources. And if we kind of look into the code of this MySQL validator that is running in our MySQL namespace on the cluster, we will see something like that. A validate function, which receives the request. From the request, you get here we get the resource. In this case, if it's a stateful set or it's a custom resource, you will get what you in this case, I made it wrong because it's a MySQL resource. Sorry, this is a typo. And yeah, in the first step, I take the object. In the second step, I validate something. In my case, I'm ensuring that the DSN contains our company name, for example, acme.co. Okay, but it could be any kind of logic that you can run at this moment. Some logic that you cannot put in the schema, in the Open API schema. There are things like more complex logics that you cannot define in this schema. So here, if the DSM match with our company name, then we return true, which is accepting our resource. If not, is rejecting. Okay, the control the object, and then the resource is not going to be created. So these are the two approaches that I wanted to explain, and then from these capabilities, there has been built several ways, several kind of building blocks in order to provide a ways to create your platform, right, with Kubernetes. And this is kind of a diagram that I want to, like a topic diagram where you can build your own platform or platforms in this case. And this is something that you can build with this today. Like if you see in the top right corner, there's a management platform, which will be our cluster, our platform that will manage the rest of the cluster of platforms. Okay, depending on how do you want to call it. And in this management platform, we run something that will show you. Something that we'll show you later, which is the app platform. That is open source thing that we have built to manage apps through different clusters. And also there is a cluster controller, which is the one that, like a building block that helps you to create and delete clusters or platforms. So here we have different platforms for different kind of areas, like web services, machine learning, serverless. And in each of those platforms, we will run different type of applications tooling. Some of them could be the same, some of them will be different, depending on the necessities. And also at the same time, we want to kind of integrate with software as a service that provide our cloud providers. So for example, we don't want to write our own CDN, and we want to leverage in the Google Cloud CDN. So with the same platform, the idea is you can provide access to the Google CDN easily in the same way that you create a database. So I will show you later how it can be done. But yeah, this will be an ideal topic world that you can build today. Next.
Yeah, and the first building block, and this is something that really very, very few people already do, is basically managing your Kubernetes clusters with a Kubernetes. And this is something that we started from the get-go. I think when we started in 2016, we were always, okay, we have to use this also for ourselves, because why should our customers use it and we should not? And there was these nice ways to natively extend this. And roughly, I don't know, 2-3 years ago, Upstream also started this effort of having a unified declarative consensus of how to manage and create Kubernetes clusters. And it is a set of CRDs, so it is an API, but it's just not just an API, but it's also reference implementations or actual implementations with which you can already start clusters on a lot of providers. And a lot of companies are involved in this. And if you've heard of EKS Anywhere, for example, under the hood, it's Cluster API, Google Anthos, Cluster API, VMware, Tanzu, Cluster API, and AKS even is working towards Cluster API. So this is something that is like driven by a lot of companies, including us. And you can already see that it's supporting quite a few infrastructure providers. And the big ones here, or the kind of most mature ones, the most mature implementations currently would be AWS, Azure, and VMware. Also because VMware is a very big maintainer and contributor in this space. But you also see Hetzner, OpenStack, AliCloud, all kinds of other providers. And it's actually quite straightforward to build your own provider on top. Like the Hetzner provider was a side project in the beginning of one of our architects, even if you're not really using Hetzner, but it was a good learning project, for example. And the interesting part of it is it's actually modeled very similar to how other things in Kubernetes are modeled. And if you've been using Kubernetes, you know the pod and the deployment and the replica set. So deployment owns replica sets for each version. They own the pods, they create the pods, and they manage them for you. And in a cluster, you can say it's the same thing. You have machines, and maybe you have something like a node pool. So you want to have a set of machines. That is a machine deployment. And they're in a certain version, so you need a machine set to manage them. And if you tell the machine deployment, I want a node pool with, I don't know, 5 workers, then that's going to be managed for you. You give it a version of Kubernetes. And if you want to upgrade the Kubernetes version, for example, you just change the version field. It's going to create a new machine set. And it's going to roll through machines similar to how you have zero downtime container upgrades. You get them also for your machines. So it's it's quite nice, and you see how the concepts are very similar. And if you're thinking of building your own extensions, that's also something to keep in mind for your users. If you build extensions similar to how Kubernetes concepts are already working, then your users will have a lot easier time to get and understand your concepts and your API.
The next building block will be the app platform, which is our own project, our own open source project that we develop in Genswarm in order to be able to manage app for the customers. So the idea was create a multi-cluster structure that we can, from one management cluster, kind of manage of the lifecycle of the apps in different overload clusters, what we call it, the cluster where we target our applications. And as it is today, it consists in 2 operators and 4 custom resources definitions. We use Helm 3 underneath for the packaging distribution of the apps. And one of the cool things of the app platform is it allows you 3 levels of configurations. So it is thought to be able to define kind of a default application configuration in the catalog. So when you create your own app catalog, you put their apps, like probably as an infrastructure role provider. You will I don't know, create an app with some basic defaults, and then for every cluster you will probably put some different configuration based on the type of cluster. Cluster can be different providers, cluster can be different sizes, different instance types. So all depend on that. You can instruct that the app will behave a bit different. And then within the same cluster, you can also could have different configurations depending if, I don't know, the application is going to run in as develop mode, or if it's going to fit for one purpose or for the other. So the idea in our case was design these 3 levels of configurations to give more flexibility for the operators and developers. In a nutshell, this is how it looks like. We have the management cluster here in the top. And then we run our first operator, which is the app operator. And this app operator is looking to 2 constant resources, the app catalog and the app CR. So the app catalog is just kind of a resource where it's pointing to the catalog of applications. In this case, it's a Helm repository catalog. And the app CR is the instance of the app that is going to be installed in one of the clusters, okay, of the workloads cluster that we call. So yeah, if you are a user and you want to install one of the applications in one of the clusters, you have to create app CR that belongs to one of the app catalogs. Our app operator will manage all the configuration, validation, and all this stuff, and will create a new custom resource which is called chart in one of this workload cluster. And in this workload cluster, for all of them, we run a chart operator, which is the one that actually install and make kind of the lifecycle of this application, right? Install, update, watch the status is right, and also report back to the app operator the state of the app in the cluster. And yeah, and that's it. Can I provide example of apps? Yeah. For example, Prometheus is one of the apps. I will show you some of the apps later, but Prometheus or login apps like Loki or the Elastic stack. We can have even Service Mesh as an app. Everything like you will install in your cluster, it could be encoded in an app. Yeah. sometimes we have even think some configurations can be also part of an app. Like, I don't know, you want to provide kind of some security policies or some role authorization rules. You can also wrap it as an app and deploy it in certain clusters. So you enforce certain rules in clusters, which are not really an apps, but at the end it will be the same. Yeah. And this is how it looks an app for us. Like we have this API version that we created. It's application.io, and this is our first version. And here you see in the spec that we need some properties to be able to function correctly, right? Our operator. One is the kubeconfig. So what are the credentials and the URL of the cluster that we want to install the app, for what catalog it belongs to. In this case, MyDB catalog, which is going to be the name of the app. In this case, Postgres, SQL, the name that we choose, and in which namespace is going to be installed. In this case, is store. And then we have two options. This is a bit the three levels configurations that I told you before. One is the one that provide the catalog, and then you can define here these two different configuration values, which at the end will be parse everything in one block, and it will be provided to the chart operator, the operator that runs in every cluster, to make the real installation. And together with the configuration, we have also the version, okay, of the application. So this is the example of our app platform, but there is plenty of building blocks out there. At the end, most of the community, like the cloud native landscape, most of the projects are relying on the same principles. So, for example, we have service meshes like Istio, observability tools like Jagger or Prometheus, even storage providers like Rook that are using operators, are using CRDs, are using admission controllers, are providing you plugins for Cuba Ctl, and they are kind of leveraging on that extensibility to make easier to control these applications. So, you know, when you install Istio and you have to upgrade it, it's not an easy task. So if you have an operator there which is encoding all the logic to make this upgrade work successfully, then it's better that you have it to read in a manual to see how you can upgrade from the control plane of Istio from one version to the other, right? So yeah, we are seeing more and more this approach take it into the whole cloud native landscape, but also in the cloud providers. So the cloud providers has really rely on the same principles, and we have seen that many of the services that they provide as a software, they are being also kind of offer in a controller CRD way, like in this operator pattern. So, for example, we have the AWS ACI project, the framework, which provides you a set of controllers that will manage all the services that the AWS provides you. Not all, but almost all. And it will abstract you from the API, the cloud provider API. You don't have to deal with, you know, I don't know, creating a bucket, a S3 bucket, or deleting it, or configuring. Everything will be at the end a CRD. And then all you have to do is kind of define how the S3 bucket will look like, and then the operator that is running behind is going to create this bucket for you and serve to you in the way that you need. At the same time, the goal of the cloud provider is kind of optimize this for production. But at the same time, these are community-driven projects. I think I'm not sure about the Google connector, config connector, but for AWS Azure operator, this is open source, and you can contribute if you want to open a issue or make a pull request, you can. And one of the things that I think is pretty cool is they auto-generate the code with the SDKs. So I don't know, in AWS you have all the APIs in the Go SDK, right? And they are able to kind of generate the controllers or the spec of the objects from the API, which makes easier to maintain the code. And then finally, I wanted also to mention the project Crossplane, the open application model, because it's kind of an effort for different companies to abstract a kind of framework. And the goal here is being able to provide you a way to operate a platform. So it's the kind of defining different roles, the infrastructure provider, the application operator, and the application developer, which is defined in the open application model, and is the one that is used to build Crossplane. And then the idea is we will have a role of the infrastructure provider role, which will kind of create the infrastructure that the platform will need. And it will be encoded in this Kubernetes style with CRDs and operators. And then there will be application configuration, application operator, which is the one that will provide the SAT configuration to run an app. And then there will be the application developer, which is actually the one that composed the app. And the thing that I like it from the project is that it will work kind of cross providers. So it's abstraction upon the providers, and it comes with a new concept like composite resources, which is kind of cool because you can create your own resources, or as an infrastructure provider, you can create your own resources that then the others can use. Using the same kind of paradigm of the Kubernetes CRDs. I think, Pooja, your time.
Yeah, I'm seeing we're almost at time, or we are at time. I'm sorry that we are taking a bit too long. I'll keep this short and to the point. The point is that there is a lot of people working on extending Kubernetes, and you see that like for bare metal, for OpenStack, Cloud Foundry is on Kubernetes. A lot of telcos are working on network function visualization. And you see actually a lot of platforms being built also out there, like the new DigitalOcean app platform PaaS is built on top of Kubernetes. Right? And what I think is most important here or most interesting here is also if you're a SaaS provider or an ISV, I see we have some friends from eSpirit here, you're running on Kubernetes. And then it's really interesting to think about, okay, could I extend Kubernetes to automate my instance deployment? Could I for each new customer, spawn up a new instance, either within a multi-tenant cluster, or do I need that much isolation that I just spin up a cluster directly with everything that I need? And we're seeing that a lot in the market also with new observability solutions like Opstrace, for example. So this is where we're going into this vision, and we're still in early days here, to be honest. There is still a lot of the standardization, especially, is alpha. I mean, extending Kubernetes is around for now 4 or 5 years almost, but the standardization is really alpha. And because not many people have extended Kubernetes, the user experience is also quite challenging still, and not many people have thought about how to make it nice and how to make it easy to use for customers or for your users. But still, we do strongly believe, and I mean, we're betting our company on this, that Kubernetes is here to stay, and it is further going to establish itself as an interface for infrastructure. If you look at recent KubeCon talks, you're going to see a lot of places where Kubernetes is used in a very surprising way and in really nice manners, and standards will be establishing itself. So the vision that we kind of talked about is not one tool to rule them all. It's you can choose your tool, you can choose Terraform, you can choose GitOps, Flux, Pulumi, But if you have a consensus API, like let's call it the Cloud Native Management API, for example, based on Kubernetes, then there is one place where everything comes together. And even if you have different teams in a very big company that have a different need for their tools, or you have maybe the IT people being more Terraform and the others being maybe some more platform teams wanting to do to Argo CD or some Jenkins because they're used to it, you can give them that choice because in the end, the API is still the same. And similar to how we went from servers to as paths to servers as Ctl, we're currently moving from clusters as paths to clusters as Ctl, and hopefully at some point also to platforms as Ctl, where you can spawn your platforms and make them really configurable for everyone. Thank you.